Hello, everyone, and hello, everyone. Just would like to start our summer 2021 quarter, and this is a class. I'm going to pre-recording all my video here. We're going to start from chapter E. The E means the essential chapter. So I'm going to go through each individual chapter and all the important parts here. All right. Right. Now, essential chapter here, if you have already have high school chemistry, this is supposed to be really a review for you here. So we're going to go through the chapter E, essential chapter pretty quickly. Then we're going to move forward to the atoms and all the periodic table, and we're going to go through that something called quantum mechanics model here. Once we have that model built up, and we're going to go through something called electron configuration. And after we understand electron configuration, we're going to talk about periodic property of elements here. So once we have all the foundation of an atomic model, electron configuration, periodic trend here, and we'll move into the a topic involved with bonding. And our main discussion is going to be focused on something called Lewis diagram here. Then after that Lewis diagram, after the valence band theory, then we should understand what hybridization, what sharing of an electron, their main principle. So that will cover up our first half of a lecture. So after that, then we're moving to chapter 7, chapter 8, and chapter 9, which is all the inorganic part. And chapter 7, chapter 8, and chapter 9, and we're going to talk about all the chemical quantities, about stoichiometry. And chapter 8, we're going to talk about different types of reaction. Sure, we do assume you understand how to balance the chemical equation. And the end of the quarter is going to be a discussion of thermal chemistry. Now, remember, that is a thermal chemistry. That is not quite a thermodynamics yet. We won't touch it thermodynamics until our second quarter. All right, so here we go. We're going to start with measurements here. When we talk about measurements, what involves a number here, and there are two different types of observations, something called qualitative, something called quantitative. We tend to use numbers because it's called quantitative. I think the number is more, it is a lot easier for people to understand. Is it shorter? Is it longer? This is a faster? This is slower? This is a warmer? This is colder? So numerical value is a lot easier, especially when we are in a chemistry lab here. We have a glassware and we can measure, yeah, this is 200 milliliter, this is only 150 milliliter, and this volume is a 10.1 milliliter, the other one volume is a 5.6 milliliter. So we can easily compare that to able to see their differences. So we're able to find out their precision and accuracy. So I'm assuming you guys are very, very good about precision and accuracy. Precision is compare the data among themselves, all right, to see how far they are away to each other here. That's something we call precision. The accuracy here is we compare the data point to the true value. That's called accuracy. Okay, so again, I forgot to mention about qualitative observation. Qualitative observations are more on a more concrete part here. Maybe we're talking about their changes of color, the change of physical states, how reactive this element is. We don't really have a numerical value to show for that. And what are the measurements? Measurements are involves numbers here. Now, whenever we talk about numbers here, it's quite important we include that units here. So it's really, really important you understand that units here because 10.0, 10.0 what? Is it 10.0 kilogram or 10.0 pound? That's a big difference here because I weigh 200 pounds here. If I don't have the units here and 200 pounds and 90 kilograms, that's about the same thing here, right? But if you don't have the numbers here, then you won't know which one's larger and which one's smaller here. So carry out the units is so important in our chemistry or in any kind of scientific field here. Units is important here. Um, Whenever we have measurements here, and I think one of the session toward to the end of lab report, I'm not talking about, I'm going to ask you to write this kind of lab report when you are moving to more advanced course here. Writing a lab report is really, really common. And on the last part of a lab report, and the teacher tend to ask you to discuss errors, something we call error analysis. And whenever we have an error here, we have something we call systematic error versus a random error here. The systematic error is something you are able to identify. The random error, and those are the error really very, very difficult to identify the source. Okay. This is a page about standard units. And we'll usually in the beginning of a chemistry class, we tend to just say length, mass, and time. Those are our standard units. But keep that in mind here. Besides the length and mass, and time here, we have a temperature. Yeah, we tend to um, told that temperature is just a Celsius or Fahrenheit, but our standard temperature in the scientific field is something called Kelvin. Kelvin is something we call absolute temperature. Absolute temperature. And there's a mole here. I'm pretty sure you guys understand what moles is about because you learned that in the high school chemistry or previous chemistry class. Moles is a amount of a unit we use to describe the amount of substances here. So it's very important. 6.022 or 6.02 times 10 to the 23rd units here. We don't use electric current for this quarter and save that electric current until the third quarter Chem 1C class here. Um, Again, matrix system is something we tend to use in science course, even though in America we don't really use matrix system that well. But I just want you to know that matrix system is really a universal thing here. Remember when we every 4 years we in the year of Olympics, we talking about running 100 meter. We're not talking about we running 110 yard, right? So we're talking about 100 meters, we're talking about 200-meter running, we're talking about whenever we deal with track and field, we're using meters here, right? So that's why it's important. There is a prefix we can use to add in from that any units here. So just want you to get that understand. So this is a page you should remember. Try to memorize that. I'm pretty sure you guys already did. Big M is a mega. Remember, I mentioned that big M here because the little m is called milli, and big M there is conversion here. Big M is equal 10 to a 6 a million here. But if you talk about little m is 0.001, which is 1 over 1,000. So be sure you understand that difference here. Something called micro, micro is a symbol here. It's like a U has a long tail. That's called micro here. And, nanotechnology was really a popular division of science in 10, 15 years ago. Nano is 10 to a negative 9 here. I just want to mention one more prefix is something called angstrom. Angstrom, a symbol for angstrom is an A, has a little zero on top of that A, that's called angstrom. That angstrom has a power of 10 to a negative 10. So angstrom is equivalent to 1/10 of nano here. So just want to let you know, please do add that one more thing there. There's a pickle second here. There's another thing is even smaller than pickle here. We call femtos. This is not on the slide. I'm not going to require you to know that. So make sure you understand all the prefix here. Okay, very well. Now, this is a temperature scale here, all right? Just want to give you all the the comparison between Celsius and Fahrenheit and Kelvin here. But one thing I want you to understand here, they don't really have that course match to each other here. You don't say 0 degrees Celsius equals 0 degree Fahrenheit here. They're not equal. Okay. However, one thing you could know here, I'm pretty sure you already noticed that the change of 1 degree Celsius is equal to change of 1 Kelvin. So you can see that they use that example of water here. The freezing point of water is at 0 degrees Celsius. The freezing point of water at Kelvin is at 273 Kelvin. So from 0 degrees Celsius to 100 degrees Celsius here, you can see the gap is 100 degree. And from for the Kelvin scale, you can also notice that the freezing point of water is from 273 to 373. So that difference is also 100 here. But in Fahrenheit here, you can see the freezing point of water is 32 degree Fahrenheit to 212 degree Fahrenheit. The change is 180 here. So they're not equal numerically. The differences is not the same. All right, very well. And I am sharing that conversion, the formula here. This is a formula conversion between Celsius and Kelvin here, between Celsius and Kelvin here. So Celsius, you taking Celsius plus 273, you get your Kelvin scale here. So they do show you that example here. I'm pretty sure you understand that. If there's questions, please do ask me during the class time. You know, what I am doing throughout the summer year, I'm pre-recording my lecture here. I'll post that lecture periodically here, so you will know you can follow along my lecture here. Because this is just so little time to finish so much material here. You know, I had to cover 9 chapters here, and by using a class time, a lot of time is going to be require you to do some outside work, asynchronous study here. So during class time, I'll be using a lot more in class time, just doing some examples and in-class activity and labs and discussion and so on. So this lecture, that's why use your time to watch that video tape. All the lecture notes and PowerPoint, I will post on the Canvas, so you don't need to worry about that. Okay. Now you probably see that conversion in 273.15. Don't worry about that. 273 is good enough. Okay. Now, another conversion, I just want to remind you here that converting from Celsius to Fahrenheit here, Fahrenheit equal to 1.8 times Celsius plus 32. You see that 1.8 coming from? That 1.8 is the ratio between 180 to that 100 here. That's what that 1.8 is about. Okay, so 180 over 100, that's what a 1.8 is about. Okay, so remember, those two are your formula. You should know that. Okay. Any questions? And again, questions, and please do come to tell to me in my live Zoom class. Next, we're going to talk about precision and accuracy. I think In a few minutes ago, I talked about precision and accuracy, and this is how you compare the data points and amount of data points, and you getting um, a conclusion about precision. And once you compare your data points to the true value, then you reach the conclusion of accuracy. Then can data be both precise and accurate? The answer is yes. That's what the wonderful data are. But can answer be not precise, not accurate? Sure. And that's the worst of that. Okay. And I'll point out a little bit more during the lab discussion for precision and accuracy. Now, uncertainty here. Again, uncertainties always depends on the type of instrument we use here, and uncertainty um, if you're not given a type of instrument, if it's just by looking at the number, and usually the last digits where our uncertainty is. So whenever we talk about uncertainty, if we're told about uncertainty, for example, here, they have an uncertainty value of 0.05 milliliter. So when they take that measurement, 23.45, that uncertainty means that tells you your high end and low end. It tells you the high end could be 23.50, could be your low end, could be 23.40 here. Okay, so that's what so important, knowing that what uncertainty is. Next, and this is something about significant figures, and this is really important. I think this is a review for you guys, knowing that the rules of significant figures here. So generally speaking, I'm not going to go through that rules in detail. I just want to let you know, whenever you count your significant figures, significant figure is a continuous process here. One more time, it's a continuous process. So if you start counting your measurements here, you start from your first non-zero digit. That's very important. You start your first non-zero digit, then you identify your last significant digit. Anything in the middle, they all count as a part of significant figure. So when you count your significant figure, it has to be a continuous process. As soon as you identify the first non-zero, as soon as you find out what's your last significant figure, anything in the middle, they're all significant figures here. Okay, so make sure you get that significant figures. The harder part is the zero part. Sometimes the zero in the middle, that's fine, because zero in the middle, that always count. What means that zero in the end here? So that's what they are talking about here, a trailing zero here. Okay, trailing zero here. Okay. So if the zero to the right after the non-zero digit, they're not significant. For example, here, when they talk about 7,000, we don't count those as zero here. When you write 7,000, we just count as one. We just count as one. You know, back in the old days, in the 70s and 80s, my teacher told me to put a bar on top of those zero. Sometimes you may want to include that zero as a part of significant figures. So there's a way you can do is put a bar on top of zero to show that how many significant figures are there. But remember, that's just an old way to do it. All right, we're not encouraging doing anything putting bar there. So if you really want to do it, scientific notation is the only way you can avoid that. Okay. Second part of a trailing zero, if you have a zero to the right after decimal place, they are significant. So they give you that example 50.0. All right, take a look at this number 50.0 here. That 50.0, there are three significant figure here, because all the zero counts. That zero, that last zero is to the right of decimal places. So that is a significant. So that's very important. This is just one give you example here and to show you how many significant figures are there. For example, the first example they give to you is 50,003, 50003. So they are 5 significant figures. So please spend about 30 seconds to look at that slide and understand the example and understand the answers. Okay, so I'll give you a 30-second break. All right, very well. Remember a few slides ago I said you should know what kind of measurement, what kind of instrument you use here, because it's very important here to how many decimal places you need to report that. So we tend to record one more digit than your smallest increment, than your smallest mark here. So you can see this laboratory glassware. Okay, the smallest increment in this laboratory glassware is in 0.1 milliliter here. So whenever you report your measurements here, you need to report um, 2 decimal places, because of one more than your smallest marking here. Your smallest marking is in 1 decimal place. Therefore, you need to report one more, which is 2 decimal places. So please report 2 decimal places. That's why you see their record shows that 4.56 milliliter here. Okay. Got it. Okay. Remember, I mentioned that to you, scientific notation is the best way to get rid of any kind of ambiguity. So don't be surprised I asked you some significant figures here. Okay. But remember that is going to be on Chem 101 homework problem and quizzes there. I'll talk about more detail. I think for this live recording, I just want to mention more to do more on the lecture side and explain all the technical part on for the course, and I'll use that our Zoom meeting there. Okay, so this is example how many significant figures. So I'm pretty sure you should be pretty well. All right, this is on example E3. So E3, this is on page. Let me see. This is on page 11, I think. Got E3 here. All right. So 554 kilometer here. You can see those are the 4 significant figures here. So again, feel free to ask me during the class. How about when we do mathematical operation? So we're going to separate that into 2 different rules here. One rule for multiplication and division, one rule for addition and subtraction here. So just want to let you know, for when you do multiplication division, the way you do it here is the least precise measure value determines the number of significant figure in the reported answer. Okay, so what does that mean, the least precise measure value? That means that the one has the smallest number of significant figure. So when you do your multiplication division, your final answer should match to the term with the smallest number of significant figure. That's what they are talking about here. Now, for addition and subtraction, a bit different. For addition and subtraction, the value with the smallest decimal measurement determine the answer significant figure. So your final answer should match to the term with the smallest decimal places. let's say your term has one decimal place and two decimal places, and your final answer can only have one decimal place. Okay, sure. Sometimes your measurement has no decimal place, then your final answer should not have should not have any decimal place. All right, here comes some example here. Okay, so I'll leave that to you, and you can think about that. I'll just mention that to the last one. For the last one, you have a 2 figure, 2 year, 3 year. All right, so your answer should have only 2 year. Okay. One other thing here, I forgot to say here. Whenever you do your conversion, all the dimensional analysis, don't count your student figure, because you can see your dimensional analysis always involved with something over one or one over something, right? You always have a one there, right? So that's why dimensional analysis is not going to be counted for your student figure. So don't count that student figure, okay? So ignore that dimensional analysis, ignore that conversion factor here. So what you need to do here is just count that first term, 4.5 phi, converting that 4.5 phi to how many student figure you have. Because 4.5 phi, there are two student figure, that's why your answer is given as a two student figure here. All right. Next, we're going to show addition and subtraction. All right, here comes addition and subtraction. You can see that first example. So the best way to do addition and subtraction, you just try to do a line up here. Addition and subtraction, you can see that first term has 3 decimal places. A second term has 2 decimal places. That's why your answer only end up with 2 decimal places here. Then you say, Miss Lee, how would you know you're going to be advanced by 1 going to 0.6a, or just drop that to make 0.67. Now, keep that in mind. Whenever you talk about rounding off, I'm going to introduce you a easier rule here. When you have a less than 5, just simply drop. When you have the number is a 5 or higher, which in this case is 7, 5 or higher, just advanced by 1. Okay, I am not going to require you to do the even number rule or odd number rule, so that's stick with the easy rule here. Less than 5, 4, 3, 2, 1, drop that. 5 or higher, just advance by 1. Okay, so just make it easier here. Now you can see I mentioned that to you here. That first term has no decimal place. That's why your final answer has no decimal place. Your final answer is going to be 456, because there's a 0.32 get dropped because it's less than 5. Okay. Any questions here? And feel free and bring that to discussion in the Zoom class. This is a performing of the operation here. So sometimes we have a mixed operation. When we have a mixed operation, we need to do one step at a time. When you do one step at a time, please do not do your rounding off in the middle. Do all the rounding off toward to the end. All right. So I'll give you this about 30 seconds to take a look at that example here. All right. Then please do ask me during the class. Again, 2 suggestions here. Number 1, do not do a rounding off intermediate step. Do the final rounding off to the end here. Number 2, whenever you continue your operation here, make sure you carry a little bit more digits than what you need to. But every time you carry out more digits, make sure you remind yourself where you are in that operation here. So I'll leave that solution A and B to you for 30 seconds. Now move on to another example. This is another example for C and D here. Again, whenever you need to, do your operation gradually, slowly here, follow the order, make sure you get your order right. All right, very well. Next, we're going to talk about density. Quite common example here, especially in the beginning of any semester or any quarter of chemistry class, we tend to measure the density here. Density is defined as a mass over volume. And again, density is something called intensive property. This is a very important word, intensive. So intensive property, and in a few more chapters, we can talk about something called extensive property. So let's see how they define intensive property. Intensive property is independent of amount of substances. That's called intensive property. Okay. Extensive property depends on the amount of substances. So intensive property, I just want you to have imagination here. If you open up your faucet here, you try to measure the density of that source from that faucet here. No matter use 10 grams of water from that faucet or use 100 grams from that faucet here, that density is going to be the same. That's why the intensive property is about as independent of amount of substances being measured here. All right. This is just a practice problem to show you how would you calculate the mass here when you are given density, given the volume here. Now, that's a simple, right? Because the previous slide we said density equal to mass over volume. Then how would you convert to a mass? Mass equal to density times volume. Density times volume. So all you need to do is take the density, which is 13.6 gram per cubic centimeter, times that volume, 95 milliliter. Then you're going to be wondering, wow, you got two different units here. You got milliliter and a cubic centimeter. But luckily, a milliliter and a cubic centimeter, they are the same here. So that's easy. So we are done. So you can see that you got 13.6, which is 3 centimeter, 95 is 2 centimeter. So 2 centimeter and 3 centimeter. So we got, okay. So that is just our final answer, just 2 centimeter. Okay. Next, we're going to deal with the energy, what's the definition? Energy here is the physical or chemical changes in the matter result in the matter in matters either gaining or releasing energy. Okay, energy is something related to work. Okay, energy types of energy we have something called potential energy and kinetic energy, right? So energy is a force push the object here to how far we can push that object to. That is what the energy is about. Okay. Now, just on your quick another imagination here. You have let's say you got a tennis ball. I don't know. I can find my tennis ball somehow. Let's say I'm holding an object here. I'm holding an object here. I throw it up. I throw that up. And throw that up, it come down, I call that again. All right. You can see my object reach the highest point. Once the object reaches the highest point, that's where the object has the highest potential energy. So on the way down, you can see that velocity keep getting higher and higher. So right before I call this object here, you can see this kinetic energy reach the highest part. But at the same time here, the potential energy is dropping. So that potential energy has been converted into that kinetic energy. All right. Remember, again, in the beginning of my lecture, I did mention that toward to our chapter 9, we're going to talk about energy chapter. That energy chapter, we'll call that thermal chemistry energy chapter. Is not really quite that thermodynamics yet, because there are a total of 3 different laws of thermodynamics. In that chapter 9, we'll only deal with the very first one, the first law of thermodynamics. What's the definition of first law of thermodynamics? The first law said the energy is conserved. It's a conservation energy. Okay, there's no loss of energy. Energy is always conserved. It's just energy has been just be converted into different form of the other here. Okay, so the example I just show you here, when I throw that object up and that object reach the highest mark, then fall down right before I call that. So you can see that potential energy and the kinetic energy being converted back and forth here. Again, I just said that there are a total of 3 different laws of thermodynamics. The reason we call that thermal chemistry is because we only deal with the first law. This is a slide, just want to give you a head start for chapter 9, because whenever we're talking about thermodynamics, all right, and there are 2 important terms, just want to share that to you. Something called system, something called surrounding. And when we deal with the system and surrounding combined together, system and surrounding combined together, we'll call that universe. So system is where that reaction takes place. That's what the system is. So the energy just flow in and out a system to surrounding, or from surrounding to system. So one thing here on chapter 9 or a future chapter on the thermodynamics, just remember that anytime you have something go into the system, we use a positive sign. Anything you have leaving the system to the surrounding, we use the negative sign. Okay, so that make sure you get your sign right. Okay, so think about this is like your bank account. Anything you deposit into that account, that's a positive, that's credit. Anything you spend, you going out your account, your debt, that's a negative. That's the same thing. Since we have that flow of energy here, flow in or out here, then that's why we have those 2 terms here. Just want to get that across to you. Something we call endothermic or exothermic. Endothermic, endo means inside. So heat transfer from outside is called surrounding, to the inside called the system. All right. Exothermic, exo means out, going out. So exothermic means that heat transfer from system to surrounding. Heat transfer from system to surrounding. Okay, any questions here? Those are the energy units here. our matrix unit is not really in calorie or kilocalorie. That's our dietary unit here. We know our calorie really well, right? Whenever we'll pay a lot more attention to the restaurant or particular food we eat here. Say, go in and out, you try to get your double. You look at the sign, give you 670 calorie here, right? So that's why you say, wow, that's the burger is a 670 calorie. That's why you said, oh, maybe we should drop that to a double single and just use one slice of cheese rather than two. All right, then hopefully it'll probably drop to 60, 80 calorie. Or sometimes we'll say, wow, that bread is almost a 200 calorie. Maybe we should drop the bread to change into protein style. So that's why we try to figure out the calorie and so on. Remember, our food calorie is a big C here. That actually is a kcal. All right, it's a kcal, big C here. All right. So you see a little c or big C here is 1,000-time difference here. Our matrix system for energy is called joules here. It's called joules here. So joule, don't think that joule is a really big number. No, joule is not that big. Most are energy, whenever we calculate that energy for any specific compound, their thermodynamic data, heat of formation, they tend to be in kilojoule unit here. So just want to let you know, the kilojoule is widely used in joule here. Okay. Kilowatts hour, and we don't really use the kilowatts hour, and the kilowatts hour, most of the time we use the kilowatts hour is only on the PG&E statement here. We'll use a kilowatts hour. So I'm not going to ask you that conversion between kilowatts hour. Okay. The rest of the chapter is going to be talking about dimensional analysis. All right. So I'll just, pretty simple. I'm just hoping that you guys understand, because the one thing to convert that from one unit to the other unit here is the main thing here is their conversion factor here. What's that conversion factor is. So that's why it's so important. You need to carry out the units. All right. I'll leave this slide to you for about 30 seconds. They write down the strategy for solving the problem here. Okay. Whenever you try to solve that problem, sometimes our common mistake we make here is we write the wrong order of a conversion factor here. Let me give you some example here. 1 week equals 7 days. If I'm asking you to convert from number of days to number of weeks, then we know our conversion factor is 7 days equal to 1 week. Then your thinking is, shall I write 1 week over 7 days, or shall I have a conversion factor is 7 days over 1 week? So that will be important, because what you need to do here is what are you converting to? If you try to convert to weeks, then your conversion factor you need to use is 1 week over 7 days. If you try to convert to days, then your conversion factor will be 7 days over 1 week. This all depends on what you are converting to. Okay. Again, this is just to show you that how to use dimensional analysis. I'm pretty sure you guys are great, and it should not be really a problem on that. You can see the goal here is you need to cancel out your old units, which is on the denominator side. Then you are getting your new units here. That's very important. Okay. Okay. And here comes, they ask you to convert from yard to centimeter. So you need to build up some strategy. All right. how would you convert yard to centimeter? You need to convert to meter first, because from meter to centimeter is easy, because for 100 centimeter equal to 1 meter. All right, so as long as you can get the first step done, then that's fine. So again, I'll leave that a few seconds here. Okay, so here comes the solution. Convert from 1.76 yard to centimeter here. Okay, so you can see that 1.76 yard contains 3 centimeter. Your final answer should be 3 as well. Okay, that's one thing. The second thing here, when you check your answers, you know you need to be a reasonable answer here, because yard is a larger unit, centimeter is smaller unit. So when you convert from larger to small unit, your number should go higher. On the other hand, when you try to convert from smaller to larger unit, your number should go, I'm talking about numerical value, should be lower. All right. All right, here's just another example to convert from 5.70 liters to inch cube here. All right, so they're planned here to convert liter to milliliter. Milliliter is same as a cubic centimeter, but centimeter and inches, there's a relationship between centimeter and inches, because we do know 1 inch equal to 2.54 centimeter. But one thing you need to be careful here is a cube here. So that's why you need cube that conversion factor. They do highlight that type of relationship you should use. Okay. So 5.70, here comes the solution. That 5.70, there are 3 significant figures here, and you end up with a 3 here. And another thing, when you check your answers here, liters is a larger unit, convert to inches, all right, inches, and your number, that's why your number is getting higher. Okay. Okay. So this just finish up our chapter E, our essential chapter. Just give you a quick overview of this chapter before our chapter 1. Really a summary for our high school chemistry, all the measurements here. So if you do have any questions for our measurements, all right, or any further discussion, please come to my Zoom meeting. Remember, my Zoom meeting is Monday, Tuesday, and Thursday from 6 to 8. I will be using most of the class time on a little bit of discussion there and do a little bit of problems there. And we're going to talk about labs. Remember, labs, we have a hands-on lab, and we're going to do some Chem 101 assignments as well. Okay, so most of our lecture is going to be done this asynchronously. All right, very well, guys. I think you guys are great. Now we're going to proceed to our chapter 1. Okay, our chapter 1 is a chapter we'll call atoms here. Okay, and this is a chapter we're going to talk about great detail about PR table. All right, so again, so many slides. There just no way I'm going to cover more than almost 70, 80 slides here. So I'll just pinpoint some important slides and to let you know, because slides are always available for you here. all right, on Canvas. Um, you know, um, this is a chapter. It all depends on are you can call this a study of matters, or this could be a definition of chemistry here. Chemistry is really an important discipline here. Okay, that chemistry is um, some schools have the chemistry in the field of biology part. Some school has the chemistry in the field of physical science part here. I have my undergrad from UC Irvine, and chemistry is placed in the physical science department, along with physics and other engineer field. Um, However, some school like my grad school in UCLA, chemistry has divided into so many fields here. Some part of chemistry, like a biochemistry, they have more smaller division of chemistry here. And biochemistry, they put the biochemistry and molecular biology just into its own division there. And they have a physical chemistry into the physical science part. So and in their med school, they have a division of chemistry in the medical school here. So I just want to let you know, chemistry is really so versatile, and it all depends on the how you divide that. So chemistry could be really in all sort of departments here. So a lot of science majors is required to take a chemistry class. I'm pretty sure that's who you are now. The types of matter, we talk about atoms, we talk about molecules, and what's an atom? Then atoms is something we call basic submicroscopic particles. What's a molecules? Molecules is something we call two or more atoms combined together. Okay, two or more atoms combined together. And in chemistry class, we tend to study how atoms and molecules behave, how molecules and atoms behave. Okay. And we know there are three different states in the matter: solid, liquid, and gas. So I'm not going to repeat that. I think you guys know solid, liquid, gas really well. Okay. And solid, they closely pack, and solid, they have fixed volume and very rigid shape. Again, well. Liquid, they not as packed as closely as a solid, but they pretty closely packed. Liquid has a fixed volume, but they don't have shape. Their shape depends on the container. Gases has the most amount of freedom as gases, and they're free to move. All right, they're free to move. They don't, again, for the gases, which is assume that entire container as a volume of gases, because the gases is just all over the place here. You cannot, when you have a beaker here, I'm holding my cup here, that the cup has a volume of 200 milliliter, you cannot just say oxygen in that one corner. We're going to assume that entire container, the volume of entire container equal the volume of gas. This is just let me enlarge that a little bit. This is just the composition of that matter here. So matter could be broken down into two parts: pure substances on one end and mixture on the other end. So for pure substances, you can see the element and compound. For mixture, you can see something called homogeneous part and heterogeneous part. Okay. Again, those are pretty simple and straightforward. I'm not really going to talk about that much. Okay, so this is just a definition. Let me shrink that a little bit. Definition and pure and mixture here. You can read through that if there's a further discussion and bring that to my attention. For the pure substances, there are elements and compounds. And they talk about what element, what compounds are. Okay, and compounds are made up by two or more elements. And what's the elements? Elements is those are symbols on the periodic table. Those are the elements. And how many elements are there? There's about 100, almost like 120 elements or so. You know, scientists and still keep discovering more and more elements here. So who knows? By next year, we can talk about 125, 130 elements. Mixtures here, again, definition mixture, heterogeneous and homogeneous. Again, it all depends on their appearances, okay? And they talk about heterogeneous, okay? They have a definition of heterogeneous, okay? And quickly, definition of homogeneous. Again, their appearances. Do they have a uniform appearances? Do they have a uniform appearances? Okay, so when you have a sugar and water mixture together, we'll call it homogeneous mixture because sugar mixes really well in the water. When you have, let's say, grease and fat in water, you don't have a homogeneous. That's something we'll call heterogeneous. You know, sometimes the mixture and the compounds are pretty similar, but water is a compound. Water is not mixture. Sugar in water is considered mixture. The main differences between a compound and mixture here is really their composition, because compound has a fixed composition. For example, water is made up by hydrogen and oxygen. Hydrogen and oxygen give you a fixed composition. But sugar in water here, you can make any composition you want. You can dissolve 1 gram of sugar in 10 grams of water, or you can dissolve 2 grams of sugar in 10 grams of water. So anything you want. That's called mixture here. Again, this is our scientific approach of a method, all right? The key character of a scientific method: observation, hypothesis, experiment. It finally can define a law and theory. So, you know, scientists, they need to have some kind of curiosity. So after they observe something here, they have the curiosity. So they can think about, based on their observation, they can think about what hypothesis they're going to make here. So based on hypothesis, they're going to design an experiment. And whenever they go through that experiment here, they need to make sure that experiment are reproducible experiment. All right. The experiment is something will allow that scientist to decide what possible law or theories are. So the experiment need to be reproducible. That's quite important here. That experiment is not something you do it has one result and I do have another result. That experiment won't be considered working here. Okay. So this observation, okay, and I'll go through very quickly here. Hypothesis. You know, whenever you make a hypothesis, doesn't mean your hypothesis or guessing is always works or right. All right. So could be a false, and you're gonna redesign that. All right. You need to modify that, or sometimes you need to discard that as well. So don't think that it always works. Okay. Then after that, then you're going to have you can build a law, and you say, what is a law? Law is a brief statement that show the summary of observation. That's a law here. Okay. There's a theory here. Then after you have law, then you can define a theory here. Okay. A theory is something called well-established hypothesis or set of hypotheses form the basics for the scientific theory. Theory tend to have some explanation. All right. Theory tend to have some explanation. The law, they give you a summary of observation. All right. Make sure you get that. Two different things here. They're pretty close, but one is talking about summary, the other one talking about explanation here. Okay. So the main thing is the law summarize that. The theory give the underlying reasons for that. Okay. Hopefully that makes sense to you. Again, we'll talk about that whenever we have some kind of data points. We could have a qualitative data. We could have a quantitative data. So this is the page talking about qualitative versus quantitative. And again, quantitative and tend to be easier to understand and versus a qualitative one here. Okay. And just give you some something called law of definite proportion. This is a French chemist, and his summary, his observation in the law of definite proportion. He said, all samples of given compound, regardless of their source, but how they were prepared, have the same proportion of their constituent elements here. Okay. And law of definite proportion, sometimes we'll call law of constant composition here. They have a constant composition. So remember, that compound has a fixed composition. That is the main differences between compound and mixture here. Example here. Example of the law of definite proportion. Again, we just talk about water here. The water has 18 grams. The reason we said 18 gram, why is it 18? Because H is equal to 1, roughly 1. O is 16, so total is 18. So when you break down 18 gram, you're going to get 16 gram of oxygen and 2 gram of hydrogen. So they ask you what's the mass ratio between oxygen to hydrogen. Is a 16 versus over 2 year ratio. So it's an 8-to-1 ratio here. So that's what is a law of definite proportion here. Okay. In 1800, there's a scientist called John Dalton. He has a law of a multiple proportion. He said when you have two elements formed together into different compounds, you can form different ways here. You could have AB1, AB2, AB3, and so on. So let me give you a concrete example here. Let's say you have an element carbon and element oxygen combined. You could form something called CO, carbon monoxide, pretty common one. You know that we can form a compound called CO2, carbon dioxide as well. So that's what multiple proportion is about. Okay. In 1800, Dalton proposed atomic theory here. Dalton proposed the atomic theory. He said that each element is composed of a tiny, tiny particle. That tiny, tiny particle is called atom. He also said that atom cannot be created or destroyed. And he said that atom can combine in a simple whole number ratio to form a compound. Okay. So he said that atom cannot be created or destroyed. And basically, he's saying that atom is small as a tiny particle. But this mystery part has been changed that because not until late 1800, I think it's 1897 or so, it's a scientist called Thomson. Thomson proposed a cathode ray experiment. He identified a particle called electron here, called that electron here. Okay. There's another scientist I would like to mention that as well here. I just want to make sure we give that credit to that scientist. Yeah. It's on page 46 of your textbook here. It's called Millikan. Millikan proposed an experiment, find out the charge of the electron here, a charge of the electron. So Thomson is able to measure the charge to mass ratio of this cathode ray. And plus that information that Millikan proposed that the charge of the electron. So we're able to determine a mass of the electron, the mass of this tiny particle here, equal to roughly 9.10 times 10 to the negative 28 gram. That's what Thomson and Millikan conclude that about that electrons here. So just want to give you the idea here, not just only Thomson, there's also Millikan's achievement here. So make sure you read that slide 35 and 36 a little bit to understand the great accomplishment by these two scientists. So this is how they figure out the mass of the electron by, since Millikan knows the charge, since Thomson knows the ratio between mass to charge ratio here. So we're able to determine the mass here. Okay, very well. In the early model in late 1800, 1897, Thomson proposed something called plum pudding model here. Okay, he proposed this. He proposed that it's a very popular model at that time. Right? He proposed that the negative charge electron is a very small particle that held within a positive charge sphere here. Okay. So that's why he proposed that electrons are within this positive charge sphere. Okay. Not until 1909, there's another scientist called Rutherford here. All right, Rutherford, he worked under Thomson. He performed an experiment called gold foil experiment. And I just want to use this slide to show you a little bit. He used an alpha beam to shoot through that gold element here. What he has noticed here, he find out majority of particle did pass through the foil, but some particle got deflected. Okay, some got deflected, but majority gone through. All right, he used the alpha beam. The alpha beam is a positive charge. So positive charge has gone through really well. So what does that mean? He concluded that matter must be as uniformly appear, it must contain a large region with an empty space. That's why they can go through without a problem, right? Another thing here, he also said most of volume of atom is an empty space. That you already said that. And he said there could be some negative charge electron outside that nucleus here as well, not within that positive nucleus here. Okay, because he said the reason they get a small percentage deflected is because those positive particle must hit the small region here. That small region is turned out to be that nucleus there. So once the alpha beam shoot through that nucleus, they're going to get deflected because we know that similar charge get repel each other here. Okay, so he conclude two things here. He said there is a small area with a positive charge. That small area turned out to be a nucleus, and eventually that he conclude that the particle inside that small area is defined as a protons here. Is defined as a proton here. So 1909, Rutherford was given a credit for discovering a proton. Neutron was discovered in 1932 by the scientist called James Chadwick here. Okay, so neutron has the mass is about same as a proton, but neutron has no electrical charge. Just want to show you the comparison of those three particles here, so we know how small, even though we say they're similar and so on. Just want to give you an idea here. Mass of proton and neutron is about the same, but neutron is slightly larger, slightly heavier than mass of proton, and electrons way down, way smaller. Okay. One thing here, if you don't remember that the number here, 1.672 or 1.675, and I just want you to remember that number. If you assume that mass of electron equal to 1, and mass of proton is about 1,836, and mass of neutron is about 1,840. So what our conclusion here is electrons located outside nucleus, and proton is inside nucleus, and neutron is also inside nucleus here. So just want to give you the idea here. Where are they located? Who discovered them? I don't care about the age, but I want you to know the chronological order here. Electron was discovered first by proton and neutron. Remember, they're all very they knew each other on the scientists. You can see that electron is Thomson, proton is Rutherford. Rutherford worked under Thomson, and Rutherford, by the time neutron about discovered, and Rutherford and his student, postdoc student, James Chadwick, worked under Rutherford. Okay, very well. Elements in PR table, all right? Page 51, this is our PR table, all right? Again, I mentioned that to you. There are about 120 elements or so. Let me enlarge that a little bit. On the PR table here, we have a symbol. We have a symbol of an element in the middle, and we have a name underneath. And we on top that number is called atomic number. And we have that symbol for atomic number. We'll call that Z as atomic number. Z is atomic number. Okay. Elements, they are arranged according to atomic numbers. So you can see 1, 2, 3, 4, 5, 6, 7, 8. So when they arrange together, they have a vertical arrangement. They have a horizontal arrangement. So far total, they have 18 vertical line from 1, 2, 3, 4, all the way to 18 of far right-hand side. So far there are a total of 7 horizontal line. Horizontal, we call them period. Vertically, we'll call them groups. Period and groups. Very well. All right. Conventionally, we don't write it this way. Conventionally, we tend to write a symbol, and we tend to give you 2 numbers here. One is on the upper left-hand corner, one is the lower left-hand corner. That conventionally, upper left-hand corner give you the information we'll call mass number. Lower left-hand corner will give you information atomic number. So this example here, all right, this example here has a neon, we'll call them neon 20, we'll call them neon 21, we'll call them neon 22. You know that 10, 10, 10, that 10 just optional information, because when you look at the neon must have 10 protons, because the element has a 9 proton must be fluorine, the element has 11 proton must be sodium, Na here. So whenever you change the number of proton, you change the identity of the elements here. So that 10 is really optional. That mass number is important because this is what the definition of isotope is about. Atom with the same number of proton, but different number of neutron. Okay, same element or different number of neutron. That is the definition of isotopes. Isotopes, because the neon 20 has a 10 proton and 10 neutron. Neon 21 has a 10 proton and 11 neutron. Neon 22 has 10 proton and 12 neutron. All right, so this is how we write conventionally. All right, our representation, we write the symbol. There's a mass number upper left hand corner, lower number on lower number for atomic number. Okay. Again, we'll still talk about neon here. This chart here just want to show you the natural abundancy of this isotope here. Okay, the neon 20 account for 90.48% of that entire element. Neon 21 account for 0.27%, only a quarter percent. A neon 22 account for 9.25%. You can see the sum of all the percentage added to 100%. 100%. Okay, so this is what, like, when you guys look at your assignments on Canvas, all the percentage of your assignment group should add to 100%. That's how we weigh each assignment. When we are involved, whenever we're doing the compounds, we could have something called ionic compound, something called covalent compound. The ionic compound is made up by ions. What is an ion? Ion is anything with a charge, we'll call them ions. So ions are involved with something called losing or gaining electron. Remember, the ions, the protons still did not get changed here. Proton remain the same. This is because you are losing or gaining electrons here. When you are losing electron, once you lose the electron, you become a positive charge. Once you are positive charge, you are called cations. Now, keep that in mind. Every element is considered neutral. So neutral means that you have an equal number of proton and electron. So once you lose the electron, you become positive charge because you have more proton. That's why it's more positive charge. Now, once you are gaining electron, you become negative charge. Gaining electron, you become negative charge. And that's why we call anions, cations, and anions. Okay. So this is give you examples of atomic numbers and mass number and their isotope symbols as well. Okay. Any questions? Feel free to bring that into my Zoom lecture. Then you say, Ms. Lee, how do we calculate, how do we determine their atomic mass? Personally, I like to call that word average atomic mass. How do we determine that? Okay, here comes the formula here. How to determine the atomic mass of an element is equal to fraction of first isotope times the mass of the first isotope plus fraction of second isotope times mass of the second isotope plus fraction of third isotope times mass of a third isotope, and plus fraction of isotope 4 times mass of isotope 4. So, well, if you have more isotope, keep adding it. Okay, so basically you take whatever percentage that first isotope occupy times the weight of your first isotope, plus whatever weight you have on the second isotope times the percentage your second isotope. Keep adding it until all the isotope has been counted. Okay. So definitely you will see that questions on the test where can one assignment here. So this is what the example is about. Chlorine, you have 2 isotopes here. The first isotope we call chlorine 35. Chlorine 35 has a 75.77%. Chlorine 37 has a 24.23%. And how do we calculate the average atomic mass? All right. So let me give you one minute here so you can take out your sheet of paper and try that. And I'll show you on slide 56 in 1 minute. All right, very well. All right, here comes the solution. We'll take a fraction of first isotope times the weight of first isotope plus a fraction of second isotope times the weight of a second isotope. We add it together. So this is our average weight of that element, chlorine, 35.45. All right. Then you say, Ms. Lee, is any instrument determine that percentage of natural abundancy? Yeah, just want to introduce you that instrument here. This instrument we'll call mass spectrometer here. This instrument, all right. So the mass of atoms and their percent abundancy are determined by using this mass spectrometer here. Okay. So it's a technique that separates the particle according to their masses here. So you can see on the bottom of that chart here, they show you, they separate their particle here. Based on the height of the peak, they can indicate the relative abundance of each isotope here. So you can see that's why the chlorine 35 is about 3 times a chlorine 37. If you remember the example we give to you, that chlorine is what? chlorine was, I don't quite remember what fraction of chlorine is. Our fraction of chlorine is 75%. The other one is about 25%. So that's really a 3 times here. Okay. All right, very well. Now we're going to switch a little bit here, switch our gear a little bit here, and we would like to introduce you something called mole here. A mole here, because there's just so many particles here that our old number system, our dozen, our counting system don't really work here. A dozen means a quantity of 12, a gross means a quantity of 144. They're just way too small. So that's why scientists invent that unit here called a mole here. How big is a mole? A mole is equal to 6.022 times 10 to the 23rd units. So mole could be associated to any units. This number is something we'll call Avogadro's number. Avogadro's number. Okay. 6.022 times 10 to the 23rd units here. It could be associated to anything. All right. So that original textbook definition is this. The value of moles is equal to a number of atoms in exactly 12 grams of pure carbon-12 atoms. That's what a mole is. But can you imagine one day you are making 1 mole of dollars? How much is that? It's a 6.022 times 10 to the 23rd dollars. It's 6.022 times 10 to the 23rd dollars. That's how big a dollar is. Okay. Next. How would you convert atom to moles and mole to atoms here? You know, the conversion is important here because 1 mole is equal to 6.022 times 10 to the 23rd atoms. And 6.022 times 10 to the 23rd atoms equal a mole here. So when you try to convert atoms to moles, you divide by 6.022 times 10 to the 23rd. When you convert from mole to atoms, you multiply by 6.022 times 10 to the 23rd. So this is what our dimensional analysis will come in to carry out that units here. All right. So let me see, I'll give you an example here. How would you convert from 2.45 moles of copper to number of copper atoms? Again, you are converting from mole to atoms here. You need to multiply by Avogadro's number 6.022 times 10 to the 23rd. So that solution here is 2.45 moles multiplied by 6.022 times 10 to the 23rd over a mole. So you can see a mole cancel out. You end up as 1.48 times 10 to the 24 moles here. Okay. So make sure you get a flow chart right. When you convert from mole to number of atoms, you need to do multiplying by Avogadro's number. On the other hand, when you're converting from atoms to mole, you divide by Avogadro's number. Next, how do you convert from between grams and moles? All right. One thing here, you try to convert from gram to mole. The key here is we need to understand what the molar mass here. We need to understand what their unit price is about. When you go to Safeway, you try to buy a Fuji apple, you try to buy 2 pounds of Fuji apple, you need to know what the unit price of Fuji apple is. Fuji apple is $2.99 a pound here, so you need to pay almost $6 for that 2 pounds of Fuji apple. And how did you find out? You take 2 pounds, that's what your weight is about for that Fuji apple, times the unit price of $2.99 per pound. So you multiply, you end up with $5.98. So you need that unit price of molar mass. All right. One thing on the boldface on this slide here, the molar mass is in grams per mole, which is numerically is equivalent to the element's atomic weight in atomic AMU here. Okay, so if you look your periodic table here, carbon is 12.01. One atom weighs 12.01 AMU. 1 mole atom weighs 12.01 grams. Okay, so that's what your AMU and moles is about. Okay, so make sure you know how to convert from one to the other. Okay, this is a great flow chart. Just want to show you how you go from grams to number of atoms. All right, if you try to go from left to right, convert from gram to moles, you need doing division divided by atomic mass. When you convert from mole to number of atoms, you need to do a multiplication, multiplying Avogadro's number. So follow your arrow through, okay? So I'll leave that flow chart to you for a quick 1 minute. So make sure you read that chart. Okay, very well. All right, let's see about this. How many copper atoms are there if you have 3.10 grams copper? We try to convert from grams of copper to number of copper atoms. So we need to convert to moles of copper first, then convert from mole to number of copper atoms. Okay, so grams of copper, when you convert to moles, we need divided by atomic weight of copper, divided by. So you can see our conversion factor is 1 mole over 63.55 grams. Once you have moles, then you need to do a multiplication, multiply by Avogadro's number over 1 mole of copper here. Okay, let me show you the answer on the next page. So take your time, 30 seconds about here. So you can see we start 3 significant figure 3.10, then we should end up with the 3 significant figure 2.94 here. Hopefully that makes sense to you. All right. How about you going the other way around? The previous flow chart, we have going from right to left. Now we're going from left to right. Now we're going from number of atoms, convert all the way to grams now. So when you have a number of atoms here, you convert to moles first. From moles, you convert to grams. So number of atoms, you divide by Avogadro's number, you convert to moles. So from moles, you convert to grams. All right. So again, 30 seconds on the flow chart. Whenever you're given a number of atoms, you need to use the division to convert to moles. Once you have moles, you use multiplication to convert to grams. So the route is the opposite. So the conversion factor will be different in terms of sign. If you use multiplication before, now it's going to be division. If you use division before, now it's going to be changed to multiplication. Right. Okay. Let me give you one example here. You are asked you to convert 8.55 times 10 to a 22nd aluminum atoms. Now they ask you to convert to I'm sorry, they ask you to convert to radius in centimeter here. If you know the density here, if you know density here. Okay. So now you are given numbers and you are given a density. Now you are find a radius here. Now, if you know number of atoms, you should be able to convert to grams of an atom. Once you know the grams, the weight divided by density, you can get a volume. You can get volume. So from the volume, then your final step is to convert to radius because everything is in a spherical shape. That spherical shape is a 4/3 pi r cubed equal your volume. So key is convert to grams first, taking grams over density, you get volume. From the volume, you can convert to radius. It's a very tedious conversion here. Okay, so again, let me leave that 30 seconds to you. This is probably the longest and the hardest conversion on chapter 1 here. Okay, here comes the solution. You end up the grams on here, my cursor, then you divide by density. So you have a volume right here. You have a 1.4187 cubic centimeter. Remember I mentioned that formula to you? This is a sphere, the volume for the spherical shapes. Volume of spherical shape equal to 4/3 pi r cubed. The r is radius. So once you know volume, you can plug in solve for the radius. The radius is 0.697 centimeter. All right, I'll leave that page for a little bit longer. So today, we quickly went through chapter E, that essential chapter, give you an overview of a chemistry, a measurement of chemistry, knowing the temperature, knowing the basic significant figure rules, knowing the conversion here, all right? And we'll continue on chapter 1, give you Dalton's law and talk about scientific method. observation, hypothesis, law, and theory. And we talk about Dalton's atomic theory, and we talk about what an atom is. And from that 1800, we'll progressively to discovery of the electron, proton, neutron, and then we're talking about isotopes, and we quickly describe mass spectrometer, show you how to calculate the isotope weight, and toward to the end, and we introduce you the concept of moles and give you idea how to convert moles and atoms and moles and grams. And this is our final example of chapter 1.8 to convert from number of atoms to grams of atoms, taking the grams over density, and we determine the volume. And once we determine the volume here, and we can use the volume of spherical shape here to find out the radius is. Okay, so this is the end lecture of first lecture for Chem 1A, and this lecture covered chapter E and chapter 1 of this textbook called Chemistry, Structure, and Properties by Tro. And this is our official textbook for Foothill College. So feel free to email me any question and definitely see me at a Zoom meeting here. So my second lecture will be for chapter 2 for the quantum mechanic model of atom here. If I have more time, I will cover both chapter 2 and chapter 3 for my second lecture. All right, great. I will stop recording here.